Okay, page 5 of math induction. So let's see this first one. Remember, this is continuing from the previous page. So basically, the only information they gave us in the instructions was that they're true for all positive integers n. So n starts at 1. So it's basically n greater than or equal to 1. Okay, so we got this interesting looking expression. It's a summation. The term is 3i times quantity I plus 4. And we're saying that the sum is equal to n times n plus 1 times 2n plus 13 divided by 2. So for the base case, the value will be 1 because that's the first value. And if n equals 1, what do we know? So let's see. We can substitute 1 in for n, so that would be I equals 1 to 1. So it wouldn't be a summation, it would just be a term. And the term would just be 3 times 1 times the quantity 1 plus 4. So that would be 3 times 5, which is 15. And the right side would be 1 times 2 times 15. So that would be 30 divided by 2, which is 15. So it worked. So therefore, P of 1 is true. Now for the step case, if P of k is true, then what do we know? So we're going to substitute k in for n. So we'll have sigma I equals 1 to k, 3 of I plus 4, is equal to, and then we're going to assume that it's true, so we're going to put k times k plus 1 times 2k plus 13 divided by 2. Okay, so we're going to assume that is true. Now we're going to write the k plus 1 version, so that would be I equals 1 to the k plus 1 of 3I plus 4. And then we're going to try to algebraically modify this until we get this expression so that we could substitute in something like this. So let's try that. So if we look at this, this summation has an extra term relative to this one. So let's separate it into two summations. So I equals 1 to k, and the term is going to be 3i times I plus 4, plus the k plus 1th term, which would be 3 times k plus 1 times k plus 1 plus 4, which is k plus 5. Okay. And if we do that, then we see that this term is the original term for the P of k, so we could substitute in the yellow part. So that would be k times k plus 1 times 2k plus 13 divided by 2 plus 3 times k plus 1 times k plus 5. Okay. Now let's put them both over a common denominator and see if we can make it a little bit more simple. This would be plus 6 times k plus 1 times k plus 5 divided by 2. Okay. All right, and then let's see if multiplying this out can help. So k times k plus 1. We can factor out a k plus 1 here, can't we? There's a k plus 1 here, there's k plus 1 here. Why don't we factor that out? That might make things easier. K plus 1 times k times 2k plus 13 plus 6 times k plus 5 divided by 2. Let's try to simplify the part that's inside. So k plus 1 times 2k squared plus 13k plus 6k plus 30 divided by 2. So let's see if we can simplify this. So these two together would be 19k. So we have k plus 1 times 2k squared plus 19k plus 30. So now what I did was I put 2k squared plus 19k plus 30 into PolySMLT Polyroof Finder, and I found out that this factors into k plus 2 and 2k plus 15. So now look what I have. I kind of have the same thing as this, right? I have, instead of k, I have k plus 1, which is expected because I'm doing the k plus 1th term. Instead of k plus 1, I have k plus 2, which is expected also because k plus 1 is k plus 2. Finally, 2k plus 13, if I put in k plus 1 in for k, I would get 2k plus 2 plus 13, 2k plus 15. So actually, this expression here is exactly what I would expect if I substituted k plus 1 in for all the k's here. So I have proven that, that this is true. Let's see, so I'm going to put here that thus, I'm going to put the I equals 1 to k plus 1, 3i plus 4. And then on the right side, I'm going to put k plus 1, k plus 2, 2k plus 15 divided by 2 is true if I equal the kth case is true. So 3i times I plus 4 is equal to k times k plus 1 times 2k plus 13 divided by 2. Okay? So since the P1 is true and pk plus 1 is true whenever pk is true, then Pn is true for n is greater than or equal to 1. Right? And it's good. Yes. Okay. Let's move on to number 3. Okay, so let's look at number 3 from page 272. So we have this summation here, and it is supposed to be equal to n minus 1 times 2 to the n plus 1 for all integers n, 1 and above. Okay. So first we're going to take the base case, which is for n equals 1, because our n values are going to be greater than or equal to 1. So if n equals 1, what happens? Then we know that this is equal to I equals 1 to n, oops, not n, 1, of, oh, so it's not even a summation, it's just one term. And the term is, we're going to substitute in 1 times 2 to the 1 minus 1, which is 0, which is equal to 1. And is that equal to n minus 1, which is 0, times 2 to the 1 plus 1? Yeah, because that's 0 plus 1. It's 1. So 1 is equal to 1, and so it's true. Okay? So therefore, P of 1 is true. And then we're going to do the step case. So if P of k is true, what do we know? So we know then that sigma of I equals 1 to k of I times 2 to the I minus 1 is equal to k minus 1 times 2 to the k plus 1. Okay. All right. Now we're going to write this similar statement with p of k plus 1. So we'll have I equals 1 to k plus 1 of I times 2 I minus 1. So that is going to be equal to I equals 1 to k of I times 2 to the I minus 1 is equal to, oh, I'm sorry. Do you see how I'm already starting to do my strategy here? I'm going to break this down into two parts. One is a part that's going to look like this part because I want to eventually substitute this in. Okay, so the part that looks like this is this part, and then I'm going to add the k plus 1th term which is k plus 1 times 2 to the k plus 1 minus 1. So that would be 2 to the k. And now I can substitute the left addend in for the yellow part, which should make it k minus 1 times 2 to the k plus 1. And here it's going to be plus k plus 1 times 2 to the k. If I look at this, I see that there's kind of like terms here. So k minus 1 times 2 to the k plus k plus 1 times 2 to the k. So I could rewrite that as 1 plus, it would be k 2 to the k times k minus 1 plus k plus 1. So the minus 1 plus 1 cancel out, so we get 2k. See what I did here? I maintained the 1, and then I grouped this 2 with the 2 to the k, so it became 2 to the k plus 1, and then the k stayed by itself right here. So believe it or not, this is equivalent to the yellow expression. Do you see how the k minus 1 corresponds to the k? If you change k to k plus 1, then k plus 1 minus 1 is k, right? The 2 to the k corresponds to 2 to the k plus 1, because if you replace k with k plus 1, it's 2 to the k plus 1, and the plus 1 is here, right? So basically, we've done it. So thus, if I equals 1 to the k plus 1 of I times 2 to the I minus 1 is equal to 1 plus k times 2 to the k plus 1 if sigma I equals 1 to k of I times 2 to the I minus 1 is equal to 1 plus k minus 1 times 2 to the k. Okay? And so then we come down to the final statement, and since p of 1 is true, and p of k plus 1 is true whenever p of k is true, then p of n is true for which values of n? N is greater than or equal to 1, I believe. Let's go back and check. Yes, it is. Okay, so that is it for this page.